So, good morning everyone. So, in today's lecture I am going to continue, I am going to talk about two topics, namely the continuation of our discussion on the conditions for separation of variables, but most important we are going to introduce the famous Noether's theorem, which talks about the result or the relation between finding variational symmetries to the existence of the conservation laws. So, what we have is the following. We are going to talk about, we will wrap up our discussion on the conditions for separable solutions, right. So, this is our continuation of our previous lecture topic, and but most of the time we are going to spend on the topic of variational symmetry leading to the famous results of Noether's theorem. Okay. So, what have we got here? So, let me continue our discussion. In the previous lecture, we had ended our discussion on finding the necessary and sufficient condition for two-dimensional problem where the Hamiltonian can be, or where the Hamilton-Jacobi equation can be variable separated. Now, for n greater than equal to 3, it can be readily shown that there are separable separable Hamilton-Jacobi equations which cannot be reduced to the Liouville's form. For that, we have to look at another result given by Steckel. So, for n greater than equal to 3, there exists a separable Hamilton-Jacobi equation, not reducible to the Liouville's form, and for that scenario we have to look at another result by Steckel. I call this my theorem number 18, the theorem by Steckel. Okay. So, what it says is the following: a necessary and sufficient condition, for one, where one is well, let me just say this result, and I am going to see just recall what is our expression 1. So, the necessary and sufficient condition for 1, which is our reduced Hamilton-Jacobi equation. So, for 1 to be separable, is there exists a non-singular matrix U, which is also equal to UKJ, where my UKJ is a function of QK. UKJ is a function of QK, where j equal to 1 to n, and the column vector W, which is W1 to Wn, right, transpose. This is a column vector such that W is also a function of Qk, right, and such that, so these elements are such that I have the following setup: summation k from 1 to n Ck of UK1 is equal to 1, and let me call this relation 1, and summation k from 1 to n Ck of UKJ is equal to 0, and this is for j equal to 2 to n. Let me call this expression by 2, and finally summation from k from 1 to n of ck wk. This is 0. Well, now this is v, and this is the requirement. I call this as 3. And finally, once these requirements are satisfied, the Stackel's result also tells us that the separable solution. So this is, so let me call this entire block of requirement as A, and then once these requirements are satisfied, the Stackel's result tells that there is a separable solution, which is the following. So the separable solution is given by psi k, which is equal to integral of square root 2 times alpha 1 uk1 plus so on until alpha n ukn minus wk right, dqk. So this times this minus, so that is and so this is my separable solution. Let me, and finally the third block of the result also says that the matrix S, which is my U inverse. So U is this matrix that we have, is also known as the Stackel matrix. Okay, this has special significance in this result, the Stackel matrix. Okay, so before I end this this statement of this result, let me just briefly say what is 1. So 1 is the Hamilton-Jacobi equation in the conservative system. So my expression 1 is summation k from 1 to n half of ck partial psi partial qk square plus v is equal to alpha 1, right. So this is my expression. Note this. So which means the result by Stackel tells us that the necessary and sufficient condition for the system to be variable separable is that we are able to find this set of functions ukj and this column vector wk's such that 1, 2, 3, these three relations are satisfied. That gives us uk's u and w, and finally once these unknowns are found, we can write our solution in the form of these unknowns as follows. So let us quickly look at an example. So the example, I am going to continue our discussion by the same numbering that we started with from 2 lectures ago. So this time my example number is 11, and we are going to reconsider our previous case of the central force problem in this time now in 3D. So reconsider the central force problem. This was first introduced in example number 10, right, and this time in 3D, right. So this time, which means our Hamiltonian is of this form, h of q bar comma p bar. This is also equal to 1 by 2m times p1 square plus p2 by q1 square plus p3 square by q1 square sine q2, right, plus v of q1, where in spherical coordinates, q1 is equal to r. This is just one example. So if we were in spherical coordinates, my coordinate q1 would have represented the radial component r, and my coordinate q2 would have represented the angular component theta, and my q3 would have represented the azimuthal component phi. that is angle with respect to the z axis. Okay, so then for this Hamiltonian, I can quickly write the Hamilton-Jacobi equation. So my Hamilton-Jacobi equation is half summation Ck's partial psi partial Qk whole square plus V of Q1 is equal to alpha 1, right? And we have that k equal to from 1 to n. This is, we have replaced pi's by its respective del psi del qk's. Okay. So I am assuming separable solution. So we have assumed that psi is equal to psi 1 plus psi 2 plus psi 3. We have already assumed separable solutions and hence psi k's. Okay. So then I also need to mention what are my Ck's. So my C1 is 1 by m, that is coming from here, right? This quantity 1 by m appearing here, and my C2 is 1 by m Q1 square, and my C3 is equal to 1 by m Q1 square times sine Q2, right? So these are my following constants: m Q1 square, sine Q2, C2 and C1. Okay. So now once we have all these constants, we are ready to set up our Steckel's equations, Steckel equations. So the Steckel equation says, so the Steckel condition says, let us set up this matrix. So C1 U11, right, plus, so Ci's are the capital Ci's we have just mentioned. So C2 U21 plus C3 U31 equal to 1. That is the first condition, and for the rest they are all set equal to 0. So C1 U12 plus C2 U22 plus C3 U33, this is equal to 0, and plus C1 U13 plus C2 U23 plus C3 U33, this is equal to 0. Okay, well, so we have to find the solution to this problem. Note that the Steckel's result says that we need to find a solution, right? So there exists a non-singular matrix. It does not say that we need to find a unique solution. So we just need to find a solution or just one solution. There could be multiple solutions. So check if I call this system as my A. So check that we can check that U11 given by m, U21 is equal to U31 is equal to 0, and U12 given by 0, and U22 is equal to minus 1 by sine Q2, and U32 is equal to 1, and U13 is equal to minus 1 by Q12, well, Q1 square, U23 is equal to 1, and U33 is equal to 0. From here students can check that these satisfy condition A, right? Okay. So what have we got here? So now so these are my solutions. Also if we choose our Wi such that W1 is, well, W1 is m times V is a function of Q1, and W2 is equal to W3 is equal to 0, then my second condition also holds, right? So then this condition holds, then summation Ck's Wk's is equal to V. Okay. Ck's Wk's is equal to V. Okay, so then what have we got? So once we have found Ui's and Wi's, we can directly write down our separable solution. My psi 1 from the Steckel's result is integral square root 2 times u alpha 1 times U11. So U11 is m, right? plus alpha 2 times u 2 1. So, alpha 2 times u, well, alpha 2 times u 2 1, alpha 2 times u 2 1, and u 3 1 is, well, I have, let us look at the Steckel's result. I should have that alpha 1 times u k 1, alpha n times u k n. So, psi 1 will be u, well. So, k corresponds to the solution we are seeking. So, k is equal to 1 in our first case. So, this is, so this will be alpha 1 times u 1 1 plus alpha 2 times u 1 2 plus alpha 3 times u 1 3 and minus w 1, and this is now integrated with respect to q 1, right. So, u 1 1 is m, u 1 2 is 0 and u 1 3 is minus 1 by q 1 square, right, and w 1 is m v of q 1, right. Okay, so that will tell us psi 1. Similarly, my psi 2 is integral of 2 minus well, square root of minus alpha 2 by sine q 2 plus alpha 3 of dq 2, and my psi 3 is equal to square root of 2 minus alpha 2 by sine q 2 plus alpha 3. So, I have just replaced all my unknowns, all my quantities using my well. So, that is my well, we have psi 1, psi 2. This is a problem in well 3D. So, this is psi 2, well, psi 3 is something else. So, psi 3 is quite simple to figure out. So, this is minus alpha 2 by sine q 2 and plus alpha 3, and sines and psi 3 can be directly integrated to see that this is 2 q 2 alpha 3. We can directly plug in the values of ui's and we can integrate those expressions to get to this result. Okay. So, we end this example by finally showing what is our Steckel matrix. Finally our Steckel matrix S is equal to U inverse, which is also equal to 1 by m q 1 square 1 by m q 1 square sine square q 2, and this is 0 0 1 and 0 1 1 by sine square q 2, right. We see that this has special significance because it tells us the determinant of this matrix is going to tell us whether the solution we have found is complete or not. Remember, we have found a solution, not a unique solution, right. So, let me just end the discussion on this example by stating the following. Notice the Hamiltonian that we began with. Let me call this expression as B. So, saying that what we did when we were solving the Hamilton-Jacobi equation corresponding to this Hamiltonian, we set the corresponding Pi's, Ci's equal to a constant, right. Setting P1 equal to a constant leads to the so called conservation of energy. Setting P2 is equal to a constant leads to the conservation of angular momentum, and finally, setting this quantity equal to a constant will lead to the conservation of the angular momentum about the z axis, right. So, when we were solving, so which means the conservation laws, see, I am regularly pointing out the importance of conservation laws, because right now immediately after a few minutes I am going to talk all about conservation laws. So, the conservation laws associated with our Hamiltonian system B are conservation of energy, conservation of angular momentum, and conservation of angular momentum about the polar axis or the z axis, right? Conservation laws. Okay. So we saw some of the conservation laws being satisfied when we were solving the Hj equations using separation of variables. Okay, so finally I am going to end the discussion of finding the solution via separation of variables with this final result by Levi-Civita. So what this result says on, essentially it tells us a necessary and sufficient condition for a system, whether the system is variable separable in the case of non-orthogonal coordinates, that is coordinates such that the Hamiltonian has the product term of the form qi dot qj dot. So Levi-Civita theorem for non-orthogonal coordinates, right? Okay, so it says a necessary and sufficient condition, for reduced Hamilton-Jacobi is that h of q bar comma p bar is equal to alpha 1, and so this is my reduced Hamilton-Jacobi equation, and where my pk's are given to be del psi del qk's, where psi is the solution to this Hamilton-Jacobi equation. So a necessary and sufficient condition for this setup to be separable, is that h satisfies the following set of n into n minus 1 by 2 equations of the form del h del pk del h del pj's del 2h del q k del qj minus del h del pk del h del qj del 2h del qk del pj minus del h del qk del h del pj del 2h del pk del qj and plus del h del qk del h del qj del 2h del pk del pj. This is equal to 0. Okay, so where my j not equal to k are from 1 to n. Fine. So this is equal, so that is my necessary and sufficient condition. Nothing is said about the form of the variable separable solution. The result only says that such a solution exists. Okay. So we end our discussion in this setup.